I am a protector, exploring the expanses of space to keep our planet safe, and all the species that call it home. I am a healer, giving doctors the vision to create amazing new cures. And using the heart's own magnetic field to diagnose itself. I am a guardian, searching a mountain of data to keep us safe when we travel. And a sea of people to find a lost child. I am a helper, powering autonomous machines that simplify our lives. Capture our greatest adventures. And make us whole again. I am a visionary, enabling taxis that don't need steering wheels, and those that don't need roads. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere. Ladies and gentlemen, please welcome NVIDIA Chief Scientist, Bill Daly.
Very happy to be here today and share a lot of the excitement I have for the things we're doing at NVIDIA. It's a very unique time in the development of computers. And there are two major forces driving what we're doing at NVIDIA and in the industry as a whole. The first is the end of Moore's Law. During the heyday of the 1980s and 90s, conventional processors got 50% faster per year. That's a 100x improvement every decade. And that fueled a lot of what was going on in the computing industry. And we've actually come to depend on that increase in computing performance. But according to our latest Turing Award winners, John Hennessy and Dave Patterson, in their latest textbook, CPUs are now getting faster only at 3% per year. A combination of the end of Moore's Law that provided us with inexpensive transistors and Dennard scaling that made those transistors useful has meant that we now have to be inventive to get that performance. And at NVIDIA, we've stepped up by providing accelerators that continue the scaling that people have come to be used to in computing performance. So we are continuing to deliver a 50% per year increase in computing performance. And as people move their applications to GPUs, they're able to realize this gain. The other big trend that's going on in the computing world is the revolution in deep learning. Deep learning is touching every aspect of how we live, how we work, how we play, all of our industries, all of our entertainment. It's truly pervasive in how it has touched and improved almost every aspect of what we do. And the deep learning revolution has been particularly exciting because it's been enabled by hardware. The technologies that it is based on, deep neural networks, convolutional neural networks, training them with stochastic gradient descent and backpropagation, have all been around since the 1980s. But it's only been since we've had powerful GPUs train these networks that these technologies have really come into their own. What we do at NVIDIA is we take these two things that are going on, the move to accelerated computing to continue to give us computing performance in the absence of Moore's law, and the trend to deep learning. And what we do is we build very powerful accelerators for demanding applications, and then we provide complete solutions, platforms that accelerate applications in graphics, AI, healthcare, autonomous vehicles, data science, and robotics. And what I'm going to do now is walk through a number of these areas that we're accelerating and talk about how NVIDIA products are accelerating each one of them. Let me start with deep learning because it actually is the technology that's underlying many of the other areas we're accelerating. Deep learning is everywhere today. If you go on the net, it's being used in many different places. You upload a photo to Facebook, they run it through a half a dozen deep neural networks to check for objectionable content, copyrighted content, to see who's in the face so they can tag people, and several other networks. If you want to watch a movie on Netflix, it makes a recommendation to you using a recommender system based on a deep neural network. Many other applications. It's revolutionizing medicine and biology. In image analysis, it's better than trained radiologists at reading x-rays and mammograms. It's better than trained dermatologists in classifying skin lesions as being benign or potentially cancerous. It's also mining databases to help doctors do more accurate diagnoses. It's being used widely in media and entertainment, many applications. In intelligent video analytics, being able to make smart cities truly smart by not just recording images of what's going on, but interpreting those images, identifying anomalies, identifying people, identifying vehicles, and the like. Now, one thing that I'll talk a lot more about later is it's going to revolutionize transportation and basically take a very large dent out of the 1.3 million people we kill on the roads every year by giving us safe autonomous vehicles. And as I said before, the technology was there. Jan LeCun wrote his paper about convolutional neural networks in the late 1980s. The work on stochastic gradient descent and backpropagation was also there. So all the algorithms existed for over 20 years. The data that's needed to train the network was around for about a decade, but it wasn't until 2012, in the case of computer vision, that GPUs arrived and provided the missing spark that ignited this revolution that's going on in deep learning. So hardware enabled this revolution, and hardware is now pacing it. Progress in deep learning is gated by our ability to train larger networks on more data. If you look at what's happening in many different fields, in image networks, going from the original AlexNet to Inception v4 is a 350 times demand in the bandwidth it takes to train the network. In speech, going through 3 generations of Baidu's deep speech recognition systems is a 30x increase in performance needed. And in neural machine translation, over a very short period of time, 10x. So to keep this field moving forward, we have to continue providing improved performance. With Moore's law dead, you're not going to get that from a CPU. You get it from GPUs. And you have to provide this performance in a programmable way. If you build a machine which is just hardwired to do one thing, for example, to do matrix multiplies, like the Google TPU, you're limiting yourself in what you can do. There's this huge Cambrian explosion in different types of neural networks. Doing one hardwired thing is not the right solution at this point in time. We need very programmable solutions to enable us to continue to create, continue to develop new types of networks, because we're really at very early days of this deep learning revolution. So at NVIDIA, we've developed our Volta V100 GPU as the engine for training deep neural networks. And we actually thought very long and hard. We've been working on deep learning since 2010, 2011, and we debated many times among ourselves, should we build an engine just for deep learning? Should we make a chip that is very much hardwired? And the answer for us was always no. And the reason is we could actually build a very programmable engine that was just as efficient. The V100 is really an amazing device. The GPU chip itself is in the middle here, and it has stacked DRAMs, HBM DRAMs, that provide nearly a terabyte per second of memory bandwidth. Many training tasks are memory bandwidth limited. If we can provide enough bandwidth, we can manage those tasks. We also need to provide enough raw arithmetic to do the training. And so when tasked with the choice between doing a hardwired engine or doing a programmable engine, what we decided to do was both. So what we did is we hardwired a neural network accelerator inside the GPU that we call a tensor core. And what this tensor core is a very efficient matrix multiply unit, which is really what most deep learning accelerators are. What it does is it takes two 16-bit floating point matrices, two 4x4 matrices of 16-bit floating point numbers. It multiplies them together and then sums the result into a 32-bit floating point matrix. This is the inner loop of most deep learning algorithms, whether they be fully connected layers, recurrent layers, or convolutional layers. The convolutions are lowered to matrix multiply. You have to do very efficient matrix multiplies. And by building this hardwired tensor core, which does 128 floating point operations with a single instruction, we amortize out all of the overhead of fetching that instruction, decoding that instruction, fetching the operands, and we actually are as efficient in terms of energy per operation as if we'd hardwired the whole thing. So we get the efficiency of a hardwired unit like a TPU, but with the programmability of a completely programmable engine like the GPU. So we announced Volta a little over a year ago in May of 2017, and since then it has become the de facto platform for training deep neural networks. But we still had a gap in that we needed to have a better inference platform. So just this August, we announced our Turing GPU, which is actually a GPU I'm very proud of because many parts of it originated as projects in NVIDIA research that I run. Turing is just amazing in many ways, but for deep learning inference, what we did is we took the tensor core that we built for Volta, which was also already very successful for training with floating point 16, and we added to it data types specialized for inference. So that we support, in addition to FP16, we support int8 and int4. And we provide Turing in many different forms. I have a couple of them up here. If you are not power limited, I strongly recommend that you buy a Quadro 6000 or a Quadro 8000 RTX 6000, RTX 8000. Because if you can afford to burn 300 watts, 295 watts, this is just an amazing board. It is a half a teraop of int4 performance. So if you can scale your network to 4-bit integer for inference, you can do amazing things with this. What we found is that many people are power constrained. They've already provisioned their data centers, and they need a 70-watt power envelope. So here's this guy's little brother, the Tesla T4. And the T4 in a 70-watt envelope is essentially half the performance. So, roughly, one quarter of the power, half the performance, by operating at a lower voltage, what we call our max Q point for inference. Now, the way the Turing chip gets its performance for inference is by the same mechanism we use for training in Volta. This is a little animation. With Pascal, the biggest instruction we had to build these matrix multiplies out of was a 4-way dot product. We'd take two 4-element vectors and basically do their dot product. And it takes many of those to build up one matrix multiply. Starting with Volta, we had FP16 tensor cores that would do that 4x4 matrix multiply. And what we've done now in going to int8 and int4 is we can essentially do twice as large a matrix multiply at a time. And so what happens is in the time that Volta would do one matrix multiply accumulate, in int8 we would do 2, and in int4 we would do 8. Or excuse me, we would do 4 of them. And these are essentially 32 times as fast as what we were doing in Pascal. So it's a dramatic increase in the performance of doing inference. If you look at what that means at building an inference platform, I've talked to a lot of data center customers who say, oh, we have lots of CPUs laying around, we'll just use those for inference. If you use CPUs for inference, your performance is down by a factor between 20 and 36 compared to if you ran them on Turing, and your energy efficiency is actually even worse than that. even compared to our existing generation, P4, which is our previous inference solution, we have 6 times the performance on inference as we had for Int8 in P4. Now, delivering the hardware is only one part of delivering the inference solution. We have to also deliver a complete platform, a complete solution to the problem. So we provide a software product that we call TensorRT. And what TensorRT does is it takes any of the frameworks. If you like to develop in PyTorch, if you like to develop in MXNet, Caffe, Theano, it will take those and map it to any of our platforms. It'll map it to our Tesla T4 or P4. It'll map it to the, it's actually not listed up there, but it'll map it to the RTX 6000 I was just holding up. It'll map it to a V100. It'll map it to our deep learning accelerator that I'll talk about in a little while, to our Drive AGX or our Jetson platforms. And it will do this very efficiently. We have optimizations that pick the optimized kernel betting on your layers and how you're doing your deep learning. We will fuse layers together to minimize the amount of network memory bandwidth required, so you don't have to go out to memory if you don't have to. We'll try to feed the activations directly from one layer to another. And by doing all this, we wind up getting state-of-the-art performance. Now, another thing we do is we build on top of this a server that uses Docker platforms and Kubernetes to load balance across the data center. So if you have many GPU nodes and you're running different models on them, you don't have to statically allocate some GPU nodes to some models. It will dynamically allocate them and optimize the performance. And what the net means is that if you were to do this on CPUs, a typical workload would take 200 CPU servers, sort of as shown here. If you move over and you run T4s, it's not one rack, it's that one little shelf in the rack. You go from 60 kilowatts to 2 kilowatts and a tiny amount of the floor space. So to show you this, I'd like to do a little demo of how TensorRT Inference Server dynamically allocates load. So can you guys fire up the demo? And why don't you explain to us what's going on?
Okay, so thanks, Bill. So what we're seeing here is the Flowers demo running on a Kubernetes cluster with 8 GPU nodes. So notice that we have a number of nodes shown by the utilization graphs, and under each one of those graphs, you can see that each such node is running an individual model. Right now, we're handling a load of 1,200 images per second, and apparently Flowers has become a really, really popular service, so our load has just gone way up. Now, notice that we will be able to deal with this load, but only 2 pods, the ones who are running the Flowers service, those are the ones that are handling the load. The other ones, the other 6 nodes, are running a bunch of additional services. So this can be recommendation, this can be speech recognition, this can be any other one of models that actually excite and delight our customers. So what we would ideally have liked is for each one of those GPU nodes to actually take part in the load sharing process and for our cluster resources to be divided individually. So what we'll do is we'll turn on TensorRT Inference Server. And notice that the same load is being handled now by all the GPUs. Look below the utilization, which is much better. Look below the utilization, you'll see that each GPU node is actually running multiple models. And in fact, now if Flowers actually gets much more relevant, and rather than the entire country, the whole world wants to do Flower inference. And you know what? 17,500 is not enough. Let's punch this up just a little bit. Then, in fact, all of the cluster is now joining in and serving our Flower model. And when the load actually gets big for additional services, the cluster will rebalance.
Yeah, thank you very much. So you see with TensorRT, not only do we optimize the model to run on one GPU, but we optimize the distribution models around your data center. So any one GPU can be running many models simultaneously, and the load is automatically balanced. So can we flip back to the slides, please? So That's accelerating deep learning. The power and the energy efficiency of GPUs is what enabled the deep learning revolution. It's gating progress in size of models, size of data sets they're trained on, and it's delivering the world-class solution for inference. Now let me talk about what for many years has been NVIDIA's core business, and how Turing is also revolutionary in accelerating graphics. Because with Turing, in addition to the Tensor Cores, which actually are very important for graphics, I'll explain why that is in a minute, we have added ray tracing cores. I'm very excited about this. This is a project we started in NVIDIA Research in 2013. It's now shipping in product, and it's an order of magnitude improvement in how many rays we can cast per second, which enables for the first time ray tracing to be done in real-time graphics. It's a complete game changer in both how games are done, consumer graphics, but also professional graphics, how architects, auto designers, and the like do their work. So before talking about that, let me start with how we use the Tensor Cores in Turing for graphics. So we have a number of technologies we called sort of deep learning for graphics. One of them is DLSS, deep learning super sampling. And what it does is it increases the resolution of an image. So we can basically render the image at, for example, 1080p or 1400p, and then upres it to 4K. And in rendering this particular scene from Final Fantasy at 4K, we basically can achieve twice the frame rate that we had in our previous generation of graphics cards. It lets us do 4K very effectively in this technology. Many people are doing a lot of stuff with both graphics and image processing using deep learning. This is a small sample of it. If you do ray tracing and you cast only a few rays, you'll get a very noisy, speckly image like this. When Pixar renders a movie, they'll typically cast 10,000 rays per pixel. If you have a limited amount of time, instead you'll cast maybe 5 or 10 rays per pixel. You'll get a noisy image. But you can feed that noisy image through a deep network, and it gives a very clean image. Similarly, you can take a black and white image, feed it through the network, get a color image. You can basically take an image where you've removed big chunks of it, feed it through a network, it fills in those chunks, and it gives you an image you couldn't tell wasn't the original one. And you can also use it to increase resolution, going from one resolution to, for example, 4 times the resolution, and it gives you a very sharp image. Now, the other thing that's what we do with the Tensor Cores in Turing for graphics. The other thing we do with Turing is we use the ray tracing cores to, in many ways, solve what the holy grail is of graphics, which is to generate the scene not by playing a lot of tricks and texture mapping polygons, but basically to simulate the physics of how light interacts with materials to give you a very accurate, physically based rendering of a scene. And the core to doing this is called ray tracing or path tracing, where we cast from the camera, every pixel of the camera, many rays, and then we simulate how they both specularly and diffusely reflect off of surfaces until they hit a light source. And you can think of for each ray, this is a problem of finding a triangle in a haystack, because we have to find not just a triangle that this ray will hit, we have to find the first triangle this ray will hit, because it'll interact with that triangle, won't reach the ones behind it. Now you can think of the triangles as just being a bunch of points in memory. We have a triangle mesh like that. We basically have a list in memory of all of the x, y, z's, the vertices of that triangle mesh. And we have to search and find which 3 of these points are the ones that first triangle we hit are. So like most computer science problems, we solve this search problem using a tree. The tree in this case is something we call a bounding volume hierarchy, where we take space and we divide it up into cubes. So if I start out and I have a cube which is all of space, I'll basically do a search and I'll decide the first subcube of that I hit will be the one in the middle shown in this tree here. Then I'll take that cube and I'll divide it up into 8 subcubes. And I'll do a search with my ray and I'll select which of those 8 is the first one that gets hit. And I repeat this process, traversing the bounding volume hierarchy until I finally get to the point where I've hit a cube that only has one triangle in it. I go to that triangle and I do a final test to see whether the ray in that triangle hit, and if so, what the normal of the intersection is. So in conventional GPUs and CPUs, the way this is done is in software, and it takes many thousands of instructions to do that traversal. It's a complicated walk of a data structure. And as a result, this process has historically been very slow. In Turing, we have built a hardwired unit that does both the traversal of the bounding volume hierarchy and the final ray triangle intersection. And as a result, this is order of magnitude faster, despite the fact that a lot of it is memory limited in walking the data structure. There's actually a very clever cache in the RT core that keeps a certain part of that tree structure always resonant, so it can be very quickly searched. And then it has a hardwired unit that in a couple clock cycles will actually do the complicated algebra to intersect the ray with the triangle, compute the angle of incidence, angle of reflection, and cast the subsequent rays. What does this mean? It means that things are 10x faster. If you compare our performance on the Pascal generation on a 1080 Ti to a 2080 Ti, we get an order of magnitude increase on each of these benchmarks, casting rays. But this order of magnitude is actually really important because it gets us over a threshold of making ray tracing possible to do real time. And it really changes the game for graphics. If you think about a given frame time, if I'm going 60 frames per second, this is 16 milliseconds I have to render the frame. What we've done in Turing is we can run this ray casting, basically having the RT cores walk that bounding volume hierarchy in parallel with running a conventional floating point shader. We've added a lot of integer resources to Turing, so we can run the integer parts of the shader in parallel with the floating point parts of the shader. And then when we're done with that, we then run the tensor cores to do some neural network processing, for example, to denoise the resulting image, because we've only cast 5 or 10 rays, not the 10,000 needed for a motion picture quality image. In fact, the addition of the tensor cores we see as very fundamental in changing computer graphics. It used to be in computer graphics, you would write a shader that would compute the color of a pixel, red, green, blue, and various magnitudes of those 3 components. Today, you write a shader that computes the input of a neural network that computes the color of a pixel. And it's a very fundamental change in computer graphics. We're applying deep learning. I mentioned super sampling already. We're applying it to anti-aliasing. We're applying it to doing motion blur. We're applying it to doing depth of field. A lot of the effects that you used to do in very complex ways are very much unified by deep learning in graphics going forward. So to see how this works, let's sort of celebrate the 70th anniversary of Porsche by ray tracing this 911 Speedster.
The speed of light, a universal constant, never diminishing, never ending. "70 years of unrelenting progress. The Porsche 911 Speedster concept.
But it is not. This is
The speed
rendered live
of light.
with ray tracing. So you see the light bouncing off complex reflections. There are caustics coming off of some of the lights. Why don't you rotate this around to show what you can do with interactive ray tracing?
Yeah. Okay. Thanks, Bill.
So I should point out that that's being rendered on 2 of these.
Yeah. Okay. So we can change the light source, rotate the model. Yeah. Look at it. Look at the headlights. They're so realistic. Think how much time the designers spent to build this perfect position lighting. Yeah. With ray tracing, you can do it in real time. This is insane. And also, we can change materials. Look at reflections, the shadows. Look at this. Amazing.
It really is a huge leap forward in computer graphics, doing things that used to take an hour per frame to render, we can now do in real time on two relatively small GPUs. Okay, let's go back to the slides. So Turing is this huge leap forward in three ways. It's completely changed how we do consumer graphics, both because we now have the RT cores. Games are using ray tracing to do realistic reflections, realistic shadows. It's greatly improving the quality of images we get in real-time graphics. For professional graphics, for auto designers, architects, and the like, it is a real-time ray tracing GPU, which just produces amazing quality images that you used to use farms of thousands of GPUs for and take many minutes to render each frame. And then Turing also provides this universal deep learning acceleration, where it provides tensor cores that can do both training and inference faster than anything else on the planet. So it's a huge leap forward. So that's accelerating graphics. We talked about accelerating deep learning, accelerating graphics. Let's move on to accelerating science. The key to accelerating science is applications. Whether you're simulating climate and weather, whether you're simulating future energy sources, whether you're doing structural analysis, there's a particular application you run. It turns out that if you go across all of the HPC centers, these are the top 15 applications. They are all accelerated by GPUs. In fact, we have over 600 GPU accelerated applications, and that's part of the platform, is building that ecosystem of applications. So typically, whatever scientific application you need for your science, it is accelerated on a GPU. I'm very proud of the Summit machine. I've been working with our guys with the Department of Energy for a long time, starting with Titan, which was our previous machine at Oak Ridge, where I started the dialogue in 2009, to make sure our machines our GPUs power the most powerful machines in the world. Summit is currently the fastest supercomputer in the world. It's 122 double precision petaflops, and it's actually 3 exaflops of FP16 performance. So by some measures, Summit is the first exaflop machine. These flops come entirely from the 27,000 some voltas in there. The Power 9s in Summit provide very few of the actual flops. And Volta is not just in Summit, it powers 17 of the top 20 machines on the Green 500 list. This is, in many ways, a more relevant list because you can be number one on the top 500 list by writing a very big check. But to be number one on the Green 500 list, you actually have to obey the laws of physics. You have to have a very energy efficient machine. In addition to Summit, the number 2 machine in the US is Sierra at Lawrence Livermore National Laboratories. Japan's fastest machine at AVCI is based on Volta. Europe's fastest machine, Pizdate, and the fastest industrial machine is based on Volta. So it's a very broad set of machines. 55% of the flops added to supercomputers last year came from GPUs. The other thing which is really exciting about what's going on at HPC today is just as deep learning is touching every aspect of how we live and work, it's touching every aspect of science. And scientists have discovered that they can use deep learning and AI to both do better and faster simulations. They get more accuracy and get the results more quickly. Here's sort of a sampling of these. The one that I'm actually most excited about here is the one in the upper right. A number of researchers at UNC and the University of Florida are doing quantum chemistry simulations over 100,000 times faster by using deep learning. The traditional way to do these simulations is called DFT, density functional theory, which is a very complex, essentially solution of Schrödinger's equation. So rather than solve the equation, what they do is that they use the fact that deep learning can be an arbitrary nonlinear function approximator, and they train a deep network to learn the solutions to Schrödinger's equation by feeding it a bunch of previously solved quantum chemistry problems. Once they've done this, they get equal accuracy on new quantum chemistry problems 300,000 times faster. And so there's many other examples of doing similar things, where rather than solving difficult equations to simulate the constituents of a scientific simulation, people train a deep network to learn those equations, and then use a deep network as an approximation, which actually does not sacrifice any accuracy and runs many times faster. The other thing people are doing with deep learning in science is they're using it to interpret results. And they can get much more accuracy. For example, if they actually take real data about the Earth's climate and they feed it to a deep network, they get 11% higher accuracy in monitoring the climate. In many particle accelerators, they use deep learning to interpret their results. In fact, at CERN, they take so much data they can't afford to store it all. The critical thing they do is when an event occurs, they use a deep network to decide if it's an interesting event or not. And if it's an interesting event, they store it. If the deep network says it's not an interesting event, they throw all that data away. So people's discoveries of fundamental new particles or Nobel Prizes are being determined by that deep network keeping the right data. So there's a lot of exciting stuff going on with deep learning revolutionizing science. One thing I'm particularly excited about is this project, where a bunch of our researchers at NVIDIA Research are collaborating with scientists at Oak Ridge National Laboratories to take the results of a climate simulation and do per pixel of semantic segmentation on that to basically classify different things going on in the climate. And they need to meet or exceed the quality that you would get by having a human being doing the same thing, taking the result of the simulation and manually label it. And this is very exciting because we're running it on Summit, and it's the first real application to sustain over an exaflop of total performance using the Tensor Cores on Summit. Training this network, they basically achieved 1 exaflop per second of real performance. What's been very revolutionary for science is this combination of very high double precision floating point performance to do the traditional HPC and Tensor Cores to apply deep learning. And by doing the two together, we've basically been able to take a lot of scientific computations to the next level. And I'm very excited about a lot of the new science being done on Summit, Sierra, and the new machines that have been enabled by this. If you look at the progress that we've made over the years, going from a node of the Titan supercomputer, which is a machine at Oak Ridge that Summit replaced, to a node of Summit, we have 50x performance on traditional materials applications that need 64-bit floating point. But we have 150 times performance on this genomics application that can use FP16. And we're actually seeing a lot of people, even those that are not using the Tensor Cores for deep learning, using multi-precision arithmetic and yielding big performance improvements by using the Tensor Cores and that very high FP16 performance for their science. So just as in the case of accelerating deep learning, in the case of accelerating graphics, you can take what used to be a huge, many racks of CPUs and replace them with a half a rack of V100s and basically get a fifth the cost, a seventh the space, and a seventh the power of doing your science in any other way. It's truly an amazing way of moving a lot of scientific endeavors forward. So in addition to accelerating traditional science, we're accelerating data science. And this is important because it's a huge market. We announced CUDA in 2006, looking at the scientific marketplace of $9 billion a year. But a few years later, which was probably around the same time, Jeff Dean at Google developed a set of techniques called MapReduce, which many people started to use as a way of building a lot of data analytics applications. On top of MapReduce, people built columnar data structures. They used Python to write analysis tools. And out of that came a lot of data analytics that are machine learning, but not deep learning. They're things like decision trees, Bayesian models, and they're used to basically do a lot of business intelligence across many different industries. The tools that have emerged as standards for doing this are Python, because it's an interpreted language. It's very easy to write in and develop. And Python sits on top of a number of libraries. NumPy is a scientific library for Python. Pandas is a data frame library that builds columnar data structures. And scikit-learn basically gives you a bunch of deep learning libraries, or excuse me, I should say machine learning libraries, but that are not deep learning. This has for many years been kind of the standard data analyst toolkit. And recently a couple developments have happened that makes this much more exciting for us. The first was a package called Dask, which is a task-based runtime. And what it does is it takes the tasks that you use for a data analytics workload, and it allows you to run them in parallel. So now you can take the same data analytics that you've been running on one CPU and run them on many parallel CPUs. So that's getting us one step of where we need to be. The final piece of the puzzle was a package called Arrow, which basically takes a columnar memory format, which is what you need to run things like Pandas data frames. And it allows multiple different packages to interact with it in a seamless manner. And by doing this, we can basically then take Arrow, on top of it put CUDA, and then take cuDF, which is essentially Pandas, and cuML, which is essentially scikit-learn, and take your traditional data analytics workloads and now run them on the GPU. And this is really huge. The Python calls will be called down instead of calls into Pandas and calls into scikit. They're now calls down into cuDF and cuML. So we've taken these pieces and added another piece, which is graph analytics, cuGraph, and we call that Rapids, which is our data analytics platform. So with Rapids, you can take essentially the same, almost the same code you had running Pandas and scikit-learn, but now the calls go down to Rapids, and they just run a lot faster. Here are the results. This is time, so smaller is better. If you're doing the first part of the workload with his ETL, extract, translate, and load, what used to take close to 2 hours on a single CPU, and even with 100 CPU nodes, only gets down to maybe 20 minutes. We run in a few seconds. It's a huge acceleration. One DGX2 is taking hours to seconds. For the machine learning part of a typical application, this is running I think XGBoost, a boosted decision tree. It's similar. The 20 to 50 to 100 CPU nodes all still running around a half an hour, and we're running this in a couple minutes. So huge acceleration. One way to think about this is sort of what is the day in the life of a typical data analyst. Before Rapids, it looks like the clock on the left. They'd show up at work around 9 o'clock, and they would have had a data set downloading overnight. And then they would start their first ETL workflow, right? They'd write their Python script, kick it off to do the extraction, translation, and loading. And around lunchtime, they'd realize that they'd forgotten a feature. They needed to rewrite the Python code, kick it off again. They'd run that, 4 in the afternoon. They'd find, there's another problem. We got to change the Python code, start it again. Gets to be 6 o'clock. That's when they call their family, tell them they're not going to be home for dinner, and they still haven't even loaded the data. If you run this on Rapids, you can have this rapid iteration thing. What used to take these hours to do ETL is now happening in a few minutes. You don't even have time to finish your coffee between runs. And you basically get through the 3 ETL runs. You finally have your data right and loaded into Pandas, and now you can actually start training your model, validating it, testing it, and running your experiments. It makes data scientists much more productive. Now, to run enterprise scale data science requires large data structures. Large data structures require large amounts of memory. Our Tesla V100 has 32 gigabytes of HBM memory. It's a compromise made. To get very high memory bandwidth, you have to put those memories on the silicon interposer right next to the GPU. You're limited on how much memory you can put there. The RTX 8000, which is the big brother of the 6000, it looks exactly the same, has 96 gigabytes of GDDR6 memory. So you just get a lot more capacity for doing your data science. If you move to our DGX station, which has 4 of the Volta GPUs, and it's 128 gigabytes, The DGX1 is 256, and this box here, the DGX2, is 512 gigabytes. We have enough memory. We can run large models and run them quickly without having to go back and forth to host memory. So let me talk a little bit about how we achieve this scaling that applies to all of the acceleration domains that I've been talking about. This box here is the DGX2. It really is kind of a revolution in many ways. If you look what's inside it, it has 16 of the Tesla V100 GPUs, but it also has 12 NV switches, a switch chip that we developed to allow any of these GPUs to read and write the memory of any other GPU as if it was reading and writing its own memory. We don't have to marshal things into packets and go through complex software packages like MPI. We simply do a load, and we can do a load or a store to the memory of any GPU in this machine. And it goes at the bandwidth of NVLink, which is 300 gigabytes per second coming out of each of these GPUs. So the topology of the DGX2 looks like this. We have 8 GPUs in the top board, 8 GPUs in the bottom board. They each go into switches, so there's 6 NVLinks out of each GPU. Each GPU has 1 NVLink to each of the 6 switches, so it can get its full bandwidth, the full 300 gigabytes per second, to any GPU on its board, any GPU on the other board. The technology that makes this possible, again, it's something I'm very proud of. I kicked this project off in NV Research a number of years ago, is NV Switch. It's our own networking technology at NVIDIA that builds on NVLink, the technology we've had for a while. It's on GV100, and it connects GV100 to the Power 9s in the Summit machine, for example. But here it connects the GV100s to the switch, most of this chip is actually those interfaces for NVLink. Those physical interfaces take up the large fraction of the die area. That's why this chip has an unusual rectangular aspect ratio. It turns out that we're limited by the periphery of the chip for the route outs from all of those PHYs. We have 18 100 gigabyte per second connections on this chip. So 1.8 terabytes per second of bandwidth. And then the actual switch is in the middle of the die. And so again, what used to take a huge server machine to do deep learning now is one box the size of a dorm refrigerator that basically houses an enormous amount of performance, two petaflops of deep learning the performance, and it's almost 1/20th the power of doing this work in the traditional way. So the DGX2 really is a universal acceleration platform that you can use for science. It's the same GPUs that are in the most powerful supercomputers in the world. You can use it for deep learning training. It turns out that a lot of models can be trained much faster because the GPUs are very tightly coupled together with NVLink. You can use it for inference, and with the Rapids software package, you can use it for data analytics for all the rest of machine learning that is not deep learning. Well, I'm very excited about being here in Israel because this is very much a startup nation. We have this program called Inception at NVIDIA to recognize and get involved with startups that are doing things that are strategic for us in the GPU business. There are 120 Inception partner companies in Israel. To focus in on just a few, they really cover a lot of the areas we're very excited about. So for healthcare, Novellus is basically looking at analyses of mutated cells in cancers, and they're able to find things that you couldn't find any other way by applying deep learning to this problem. And they recently moved their platform from the cloud to running on DGXs and just got a huge increase in performance reduction in cost by doing that, in a large part because they avoid the bottleneck of having to load all of their data to the cloud by having a local solution. They're able to get around that. Cognata is a startup that's doing self-driving cars. They're building virtual worlds in which to train these self-driving cars. Again, they're able to take our DGX technology and get huge savings. TrackPoint is making smart shopping carts that will sort of look at the things you throw in the product. They're trying to give you a physical shopping experience that's similar to the online shopping experience. We can get interactions about the products you're putting in the cart. You don't have to scan barcodes or anything. It just knows what's in there. And AnyVision is basically building smart city technology, building surveillance technology that can do very rapid face recognition. And all of these things are leveraging our technology. We're just very happy to work with all the companies here that are doing such exciting things. So let me move on to a few more things we're accelerating. One thing I'm very excited about is our work on autonomous vehicles, because ultimately we're going to save a lot of lives. What we do is basically provide a complete platform for autonomous vehicles. And that platform includes not just what we deploy in the vehicle, but it starts with training. You have to, if you want to do autonomous vehicles, you have to collect huge data sets and curate them, label them, and then train your perception networks on those data sets. Once your networks are trained, you have to take your overall system and simulate it. So we basically train our networks both on real data and on simulated data. And anytime we make a change, we basically revalidate our whole driving platform with a hardware-in-the-loop simulation. So we basically have one box which is running, either playing back real data or running synthetic data. And the second box actually has in it our Drive PX boards, and it's feeding in either the recorded or the simulated data and basically running the real hardware that doesn't know it's not in a real car, but in the simulated world to validate that whatever changes we made work on everything we did before and on billions of miles of simulated driving. And then I should say finally, we have what we deploy, which is both our Drive PX platforms, Drive PX Xavier and Drive PX Pegasus, but also all the software that sits on top of them that provide perception to recognize cars and pedestrians, cyclists. We can find the lanes in the freeway. We can do a suggestion for our path planner, recognize road signs and lights. All those perceptual networks are part of the package that we offer. Recently, to demonstrate this technology, we completed a drive in the Bay Area, which is actually not a very easy place to drive. It's a lot of traffic. The drivers are very aggressive. It was an 80-kilometer loop on Interstate 280, California Route 92, US 101, and California Route 85. And through all the highway interchanges, doing 10-lane changes, the human driver never had to take over. So this is an interesting video. Can you guys play the video? Yes, you see the car has multiple LiDARs. It has 12 cameras. It has radars. And we're fusing all of that data together for many tasks. The first is object detection. We basically will put a box around every object. Not only are we detecting the objects, we're estimating their distance, we're estimating their velocity. We also detect free space. You'll see that there's actually a line. That's an independent network that basically, without doing object detection, senses where it would be safe to take the car. We detect lanes, and then you'll see that there's sort of this green line ahead of us. We use a neural network to propose a potential path to our path planner, and our path planner then refines that original estimate. This works robustly in all conditions. This happens to be a pretty nice day, but it will work just as well in rain or snow or day or night. And you can see that there's cars all around, and our car is doing its, changing lanes, avoiding other stuff. You'll see our chase car there, just sort of filming it.
What's the weather in San Francisco now?
The weather is 67 degrees and cloudy in San Francisco.
How about tomorrow?
There will be partly sunny skies with a high of 69 degrees and a low of 58 degrees in San Francisco tomorrow.
He's reading the signs there. You see his car is passing. It's updating not just the detections, but the free space as well, which is an independent determination of that. So I think that's really cool. I'm looking forward to having a car like that take me to work every day so I can get a lot of reading done. Now, one thing I find very interesting about that and kind of very challenging is, we have several LiDARs, we have 12 cameras. For those cameras, we feed them not into one neural network, we feed them into one neural network to do object detection, a different neural network to do free space detection, another neural network to do lane detection, another neural network to do path proposal for our path planner. Now let's consider just one of those cameras and one neural network. We tend to use ResNet 50 as our workhorse network. We have a variant of what we call DriveNet that we actually use for all of those tasks. If you were running an ImageNet-sized image, which is 225 by 225, it takes almost 8 billion operations to feed one image through ImageNet. So if you were doing ImageNet images at 30 frames per second, it would be 230 gigaops, about a quarter of a teraop. But of course, we're not doing ImageNet-sized images. The cameras in our car today are HD cameras, and they're probably going to go higher resolution in the future. To do 30 frames per second HD on ResNet 50 is almost 10 teraops. And that's to run one network on one camera. We have 12 cameras. We have 4 networks. So what do you do to provide the many tens of teraops of performance that you really need to build an effective self-driving car? And the answer is you build really efficient deep learning hardware. And Xavier is a really neat chip for a lot of ways. First of all, it has all of the goodness of Volta. We essentially have a tenth of a V100 in having 512 CUDA cores from Volta. Volta V100 is 5120. But we also have this thing called the NVDLA, which is up there on top, which is a hardwired deep learning accelerator. You get about 20 teraops of deep learning performance out of the Volta. You get another 11 out of the deep learning accelerator. It's sort of a neat technology that really lets us scale our ability to handle multiple cameras, multiple sensors in the deep learning environment. Before talking more about the DLA, I will also point out that Xavier has 8 of our own ARM cores, so we design our own CPUs, and the Carmel ARM CPUs are in many ways very superior to anything that you can get from ARM. Same ISA, much faster, much more energy efficient. We also have a vision accelerator that accelerates a lot of the traditional computer vision tasks associated with pre-processing the images before you feed them into the deep networks. Now our NVDLA, you can think of it a lot like a Google TPU. It is a hardwired deep learning accelerator, but it's much better than the Google TPU for a couple of reasons. The Google TPU is basically a big matrix multiply unit, and we have that too. It's a MAC array here. It does a 32 by 64 int8 matrix multiply, 2048 multipliers all running simultaneously. So that's great, but doing matrix multiply is pretty easy. What makes this accelerator sort of stand apart is 2 other boxes on this picture. The first is the sparse weight decompression. So it turns out that most neural networks are sparse. For convolutional neural networks, only about 30 to 40% of the weights are non-zero. And if you use a ReLU as your activation function, only about 30 to 40% of the activations are non-zero. So really only about 1 multiplying 10 has to happen. And so we exploit that sparsity in 2 ways. We actually store all of our weights and activations in a dense form with the zeros not stored and expand them on the fly into the MAC array. That's a sparse weight decompression. And then in the MAC array, we do what's called data gating. If a weight is a 0, we actually don't toggle all the lines to 0. That would dissipate a lot of power. We hold the lines in their previous state and send a separate line saying I am 0. And that actually freezes both inputs of the multiplier. So the multipliers dissipate no power in that case. It makes it an order of magnitude more energy efficient than a naive matrix multiplier like a Google TPU. The other box on here is our Winograd transform. So for convolutional networks, you're doing convolutions. And as everybody who takes a signal processing course knows, if you do the convolutions in the spatial domain, say you do a 3 by 3 convolution, that takes 9 multiplies and 9 accumulates. But if you do that convolution in the frequency domain, you can do a single pointwise multiply. So the Winograd transform is similar to that in that it allows us to do a 3x3 convolution with a single multiply. And so when you take the overhead out of it, depending on the tiling, it gives us between 2.5 to 4 times performance boost over doing the convolutions in the spatial domain. So the NVDLA is a very, very powerful accelerator. And we're so excited about it that we didn't want to keep it for ourselves. This has been open sourced. You can go to nvdla.org. You can download the RTL. You can download all the software tools, because we want to enable the ecosystem of people applying deep learning to everything, and we don't have enough bandwidth to develop all these chips ourselves. So we're giving away our DLA, and actually lots of people are using it already to do very exciting things. Now, it turns out that doing AI for self-driving cars is really hard for a number of reasons. You wind up having to collect data of a number of things, vehicles, pedestrians, bicycles, animals, hazards. The last category is probably the hardest, right? We have piles of data on cars, pedestrians, and bicycles. But when some bag falls off of the pickup truck ahead of you on the road in front of you, your car has to recognize that and make a decision. Does it run it over? Does it swerve around it? What is it going to do? We have to do this any time of the day, twilight, night, with the sun facing us, with the sun behind us. And we have to do it in good weather, bad weather, rain, fog, snow. So we have to collect huge amounts of data of all of these things and all of these conditions and curate it. And we do this for a number of different things. Our perception includes free space perception. We basically detect free space independent of obstacles. We detect the obstacles, the cars, complete with their distance and velocity. We take the LiDAR and we filter that data. And this winds up being a huge amount of data if you want to do it well. So in fact, if you want to look at what you need to run meaningful amounts of data, you have to basically take petabytes to exabytes of data and run them through the test over and over again as you change your system. So what we do is we built a data center to do this, that running 3,200 nodes, we're able to take this 24-hour test on 180 petabytes of data, basically running far faster than real time, actually many times faster than real time, to validate our system. And we do this both with total simulation, simulating these networks just on the GPUs, and with hardware-in-the-loop simulation, where we take our drive PXs, we synthesize or playback recorded data, and then basically have that drive PX actuate the steering, accelerator, and brakes of the cars and test the result. We have a complete platform for autonomous vehicles. It actually includes Drive IX, which is the inward-looking part of this. It looks at the driver. It looks at pedestrians around the car. It can recognize if the driver is getting drowsy. It detects their head pose, detects where they are looking. If they're not looking where they're supposed to be looking, it can alert them. We have our Drive AGX developer kit, both AGX Xavier and there's Pegasus. And then we have Drive AV, which is the actual deployed autonomous vehicle software, which includes both the perception component as well as the path planning and control components. Our Drive platform is being very widely adopted by numerous companies, lots of auto companies, taxis as service services, Uber and the like, truck companies, tier 1 providers to the OEMs, as well as other companies. It's being used by a very large number of people in the business. Now, in many ways, making a self-driving car is an easy example of making a robot, because all the self-driving car has to do is navigate around without hitting anything. Robots actually have to hit things in a constructive way, right? They typically have to interact with their environment. And so this is much harder. But we're also building a platform for accelerating robotics. And this starts with our Isaac platform, which basically includes a bunch of things we call GEMs that do sensor processing, mapping, and localization. They'll estimate the pose of humans in the scene. We can then take this platform, put it on this robot that we call Carter, and have Carter carry out real tasks. So if you guys could play the Carter video. Yeah, this is Jensen ordering a salad. This, by the way, is our new headquarters building in Santa Clara. It's really, really very nice building. This shows the path planner plotting its path. See on one side the simulation, and on the other side the real world. And so we can train this in simulation and then play it in the real world, and it works great. And that's how it gets delivered. So that's sort of what, thank you. That's one level of what our Isaac platform is able to do today. I recently started a robotics lab in NVIDIA research to try to develop some of the technologies that our Isaac platform will be able to do in the future. So this video, for example, shows how robots can do manipulation in uncontrolled environments where things are being perturbed by humans. Because if you look historically, robotics was a technology for very accurate open-loop positioning. And what deep learning has allowed us to do is to now build robots that can interact with their environments and react to unexpected circumstances in those environments. So if you look here, this robot is trying to manipulate a cup while a mischievous human is basically pushing it around and changing its position. And it's able to do that because it has perceptual modules that we've developed that can react to what the human does. In the next piece of the video, it needs to stack a couple cups, but the human is changing the problem on the fly by moving the cups around. And the robot, again, using its perceptual system, can react to that, find the cups, and stack them. So we've developed a lot of fundamental technologies called Riemann motion policies that enable this interactive control of the robot working with humans. Another thing we're doing in the lab is we're trying to look at how very effectively to transfer learnings from the simulated world to the real world. So you saw, Isaac navigating, or excuse me, Carter navigating through the Endeavor building, and it did that first many times in simulation before we let the real robot loose running around the building. It turns out that's a relatively simple task because it's just, steering itself around. If you're manipulating things, and in this case, the task is you have a cylinder on a string, and you have to swing it into a hole. There's a lot of things that don't match between the simulated world and the real world. Friction is different. The actual mass of the cylinder may be slightly different. There may be differences in the actuators and the gains. And so you could learn the behavior very well in the simulated world. It may not transfer to the real world. So what we did is we developed this technology where we can train in the simulated world. And then when we try it in the real world, each trial in the real world gets fed back into the simulated world to try to learn the differences. So we turn the real world one on. So it's going to try to flip it into the hole. In the real world, it doesn't go because things are different. But it takes the errors that it finds in the real world, uses that to modify what happens in the simulated world. And in a relatively small number of trials using reinforcement learning, it's able to learn how to swing that cylinder into the hole. So to enable people to build really exciting robots, we're launching our AGX platform, which includes things of various sizes, up to 320 teraops, TensorOps, starting with the small one with a single Xavier chip, up to a couple discrete GPUs. Our Isaac library has all of these gems for perception, segmentation, human pose estimation, key point finding, path planning, so you can basically build very effective robotic systems by taking Isaac, combining these gems, and applying them to your task. We have the Jetson development kit, so you can basically take sort of a Raspberry Pi sized thing, but with 30 teraops of deep learning performance that you can use as the brains for your robots. And then we have the simulator part of Isaac that you can take and use to simulate your robot and basically use reinforcement learning to train behaviors in the simulated world and then transfer them to the real world. So let me wrap up, but before I do that, I want to say one thing I'm particularly excited about today is that I'm opening a lab here in Israel. It's being headed by Gal Chechik, who will be a director of deep learning research. And it's going to be focusing on deep learning for smarter perception, and in particular being more efficient about training data by combining modalities. So we'll have computer vision, for example, combined with language. So a deep learning agent can learn the way a human does by having somebody tell it, not only is this a bird, but it's a robin because it has a red breast, and it will basically take the language and the image, combine that, and learn in some sense a more deep fashion than just having somebody label robin and stick that in the data set. So Gal, if you're here, can you stand up? So I'm very excited about having Gal on board. He's a PhD from Hebrew University and very talented deep learning researcher. And we are hiring. We're trying to get some very talented deep learning researchers. Our research labs run very much like an academic environment. We publish. We're very open about what we do. And so if you're a very good deep learning researcher, talk to Gal or talk to me. So to kind of wrap up, it's a very exciting time to be in the computer business because there are two forces that are going on that are completely changing how the computer world is working. The first is the fact that Moore's law has died, and to fill the gap, to continue to provide the demand we have for this 50% a year improvement in performance, we've had to step up and build accelerators to do accelerated computing. And we've been accelerating deep learning, we've been accelerating science, we're accelerating data analytics, we're accelerating autonomous vehicles, we're accelerating robotics. The other factor that's shaping the world is the deep learning revolution. Deep learning is changing how we do almost everything, and it's doing it in a positive way. It's making how we do HPC better by learning how to simulate things rather than actually solving the equations, by interpreting the data when we do a simulation to give us more accurate results, and giving us the perception for self-driving cars and the like. If you think about what NVIDIA is we're a company that builds accelerators, and we then build the platforms to take these accelerators and apply them to deliver complete solutions on a range of things, from graphics to robotics. So if you think about what I talked about, we have the GPUs, ranging from the T4. If all you have is 70 watts, you can still have 200 teraops of inference performance, to the RTX 6000 and 8000, which are a half a petaop of inference performance. The Volta V100, which is still the gold standard for doing deep learning training. And we can scale those up with the DGX2 that is essentially a really big GPU. The NV Switch and NV Link technologies allow us to take 16 GPUs and use them as if they were one, because they can share each other's memory with very transparent load and store instructions. Taking this powerful hardware base, including the AGX platforms we base our autonomous vehicles and robotics on, we have acceleration stacks to apply these to science, to deep learning training with cuDNN and acceleration software for every framework, not just TensorFlow, but we can do PyTorch and Caffe2 and others as well. For deep learning inference with TensorRT that optimizes the network, and then the TensorRT server that allows us to take it across many GPUs, balance the load so each GPU is running multiple models simultaneously, and then our new release of Rapids that allows us to apply all of this to data analytics, to the part of machine learning that is not deep learning. We also have vertical platforms for robotics with Isaac, and for automotive with Drive IX and Drive AV, and they provide the complete solution, not just the deployment in the vehicle, but all the technology needed to collect data sets, curate those data sets, train the networks, simulate, and what we call re-simulate with hardware in the loop. And we're building the ecosystem. We're very excited about interacting with a number of the local companies and building this ecosystem around these platforms to make the world a better place. So with that, thank you very much. I'd be happy to take a few questions.